Lesson 27 activity. In this video, I'm going to do the 6 problems that are scanned in your packet. I'm not going to do the one from your textbook. Gas is being pumped into a spherical balloon at a rate of 5 cubic feet per minute. Find the rate at which the radius is changing when the diameter is 18. Feel free to draw a picture for this one. I don't think it's going to help me, so I'm just going to jump right in. We're trying to find the rate at which the radius is changing. So that is a dr dt equals question mark. We'll go ahead and get the units up here. I see the radius is maybe going to be measured in inches, and time is measured in minutes, inches per minute. Okay, and as I was looking around for the units, I did notice this trap. This is in cubic feet, but this is in inches, so we are going to have to convert one of those. I guess I'm choosing inches the way that I've written it here, but it's okay to go feet if you wish. In fact, maybe feet is better. Let's go feet. Feet per minute. Okay, so that is good. And then we are given something else, that air or gas is being pumped in at 5 cubic feet per minute. So that is also a derivative. So symbolically, dV dt is 5 cubic feet per minute. And so that right there tells me, and also the diameter is going to be 18, but we're not going to fix that just yet. These two equations tell me I'm looking for an equation that relates V and R, the volume of a spherical balloon. Okay, so hopefully we know this one, but if not, again, I think I would give you this particular one, but the volume of a sphere is 4/3 pi r cubed. I'm happy with this one in that there's only one variable over here on the right-hand side, so nothing to do but take a derivative of both sides with respect to t. The derivative of the left-hand side is simply 1 dV dt. The derivative of the right-hand side, 4/3 pi is a constant multiplier, so it gets copied. The derivative of r cubed is 3r squared, but that r is not the independent variable, it's t, so we have to multiply by the derivative of r with respect to t. We'll clean this up just a tiny bit. dV dt equals, the 3's cancel, right? So we just get 4 pi r squared times the r dt. Okay, and what we're trying to do is plug in. Let's see, we know that dV dt is 5, and it says that the diameter is 18 when we're fixing this balloon at one moment in time. But right here, I'm trying to plug in a radius. So 2 changes here. 2 things to be aware of. So this is telling me the diameter is 18 inches, but we said we were going to go into feet, and so that's 1.5 feet. But in our bottom equation that's orange there, we've got an r, not a d, and so therefore the radius at this one moment in time is 0.75 feet, half of the 1.5 feet. So that's what we're going to be plugging in. So this one and this one go together and make one new equation. So dV dt on the left-hand side, so I'm just copying this equation down here. So dV dt, we're changing to the number 5, that's given, equals 4 pi r squared. R is now ready to be fixed at 0.75. Remember, you don't fix the variables until after you've taken a derivative. Then it's okay to fix them. So it was r squared, and then times the r dt, that's the unknown. So we just have to solve this thing for dr dt, and we are good. So we just divide both sides by 4 pi times 0.75 squared. If we want like a decimal version, then we can just type that into the calculator. We could clean this thing up just a little bit. I just looked at the key in the packet, and it does have like a fraction version of this thing. So if we chose to clean this up, maybe instead of 0.75, we wrote 3/4 here. That's what they did anyway. Then squaring 3/4 gives me 9/16. So this became 5 over 4 pi times 9/16. That's dr dt. And then the 4 and the 16 can reduce. Give me a 4 on the bottom, and then you can multiply the top and bottom of the big fraction by 4, and that gives us the answer that is in your packet. 4 gets multiplied by the 5, 20 over 9 pi, which you can type into the calculator. Turns out to be around 0.71. And we said the units were going to be feet per minute. Number 5, a light is at the top of a 16-foot pole that's marked in the picture. A boy 5 feet tall, also marked in the picture, walks away from the pole at a rate of 4 feet per second. That is not marked in the picture, but that tells me that the length of this line segment, the distance between the boy and the pole, is changing at 4 feet per second. So it feels like we should give a name to that thing. How about we call it x? And then we can symbolize dx dt is positive 4 feet per second. That length is getting longer by 4 feet every second. At what rate is the length of the shadow increasing when he is 18 feet from the pole? So I'm not going to do anything with the 18 yet. I don't want to fix that 18 until later on, but at some point x is going to become 18. And but I should symbolize the rate at which the length of the shadow is growing. And so the length of the shadow is this thing. So how about we call that one y? And it says at what rate is the length of the shadow increasing? So that means symbolically we are looking for dy dt. Okay, so let's see if we can come up with some relationship between x and y. We need some equation that relates x and y because we have these derivatives given to us here. One given anyway, and the other one we want. Okay, so what's the relationship? Well, I don't know if this is just a bad image, but I'm going to draw that line in thicker. You might have it, you might be able to see it better on your scan. But that line, actually I should make it hit the top of the kid's head. That line is going to be the one that's going to give us some triangles. So there's one big triangle, and then there's a littler triangle where one side is the kid himself. And just like in the demo from today, we have two similar triangles. The small triangle and the entire triangle are similar, which means that we get to write down a proportion. So let's do that. So I will do the y in the small triangle, and then what is the corresponding side? Actually, I'm not going to start there. Let's start with the 5 in the small triangle, divided by the corresponding side in the big triangle. So the 5 is the vertical one, so the vertical one in the big triangle is 16, equals. And now we're going to pick a side in the small triangle because we had the 5 on top. We have to pick a small side up on top over here, and so that's clearly y, divided by what's the corresponding side of the big triangle. Really common wrong answer right here is x. X is not the side, is not any side of the big triangle. The side of the big triangle is the entire side. Just like you did the entire side of the little triangle, you have to do the entire side of the big triangle. And so that is supposed to be x plus y. Not just x, but x plus y. Okay, so we could take a derivative of the equation in this current form. That would involve using the quotient rule on the right-hand side. I would rather avoid that if I can, and I can. Let's cross multiply. 5 times x plus y equals 16 times y. And you could take a derivative here, at least we've avoided the quotient rule, but we can do even better by distributing the 5 and then moving the 5y over to the right-hand side, which will get our y's together on one side and the x's on the other side. So that gives me 11y right there. Okay, that's as good as we can do. If you wanted to, you could divide both sides by 11, or you could divide both sides by 5, but I'm just going to leave it in its current form and take its derivative. Derivative of both sides of that equation with respect to t. Time is the thing that's passing underneath all of these variables. So derivative of 5x is 5, but then x is not the independent variable, so we tack on a times dx dt equals derivative of 11y is just 11, but then times dy dt, chain rule for both of those. And now I think we're good. We just have to substitute. We were given dx dt is 4, and we wanted to know dy dt, so we just plug in right now. So dx dt is 4, dy dt is the unknown, piece of cake. Dy dt, so we get dy dt is equal to 20 divided by 11. And again, that's feet per, I think it was minute. Okay, 20 divided by 11, feet per second, I should say. You can get a decimal there if you wish. And that's it. That is the rate at which the length of his shadow is changing. This one's a little bit unusual in that there was a piece of information in this problem we didn't actually use. We never used the fact that the boy was 18 feet away from the pole. Surprisingly, it actually makes no difference how far the boy is from the pole. He could be 18 feet. If there was still an x in the equation we just plugged into, we would have plugged in x equals 18. That would have helped us. But it turns out it doesn't matter whether he's 18 feet or 1 foot away from the pole or 200 feet away from the pole. The length of the shadow is going to grow at a rate of 20/11 feet per second, no matter where he is. So that's kind of a surprise. Not fast then slow, not slow then fast, but that growth rate is constant, always 20/11 feet per second. A boy flying the kite holds the string 5 feet above ground level, and the string is paid out at a rate of 2 feet per second as the kite moves horizontally at an altitude of 105 feet. See the figure. Okay, so we got the person holding the kite 5 feet off the ground, and the kite is moving horizontally, and it stays at a constant 105 feet off the ground. So it's not going this way. It is staying at a constant 105 feet off the ground. And so let's start marking this picture up. So it says that the string is paid out at a rate of 2 feet per second. So that feels like what we want to do is symbolize this distance. So how about we give that one a name? I will call it C. And we're going to recognize that the 2 feet per second is a rate of change of C. It is 2 feet per second for dc dt. Okay, so that's one thing that we know. And then it says, assuming there's no sag in the string, so that's a straight line for C, find the rate at which the kite is moving when 125 feet of string has been paid out. So I'm not even going to write the 125 right now. At some point, C is going to be 125, but not yet. It's too early. But we know that, that the kite is moving only horizontally. So when it says find the rate at which, let's assume the kite is moving to the right. It says find the rate at which the kite is moving horizontally. Is just find the rate at which the kite is moving really means what's the rate that it's moving horizontally, because that's the only movement that the kite is undergoing. And the rate it's moving horizontally sure feels like we need a name for how long this distance is, or I guess really how long this distance is. So let's go ahead and draw that in. I'm going to start not on the ground, but I'm going to start 5 feet off the ground. And I'm going to call that distance right there A. And I'm going to say that as the kite string pays out, this kite gets farther and farther away from the boy, and therefore A gets bigger and bigger, right? A just goes until the, I went too far with my A. A just goes to wherever the kite is, just like that. Yeah, I think that's it. And so as the kite moves this way, the A is just going to get longer, and it's always just going to be right underneath. And so when it says how fast is the kite moving, it's really asking us something about A. It's asking us specifically for the ADT. So how many feet per second is that A growing by how many feet per second? Okay, and so I've got two sides of a right triangle drawn in. I sure feel like I should draw the last side. So that's this one here. Not going to the ground, but going 5 feet off the ground. And you could label that with a B. In fact, when I labeled the C and the A, it's because I already knew we were going to do a Pythagorean theorem here, but it's okay. Any letters are fine. But you should not label that purple thing with a B, because that purple thing is not variable. That purple thing is fixed. No matter where this kite is in the current spot, or we could put the kite right over here, that vertical purple distance is always 100. It's the 105 feet minus the 5 feet that the string is off the ground. So there's our right triangle, and clearly Pythagorean theorem is the relationship we're going for. A squared plus 100 squared equals C squared. We'll take a derivative of both sides of this equation. T is the variable we're taking a derivative with respect to. A squared becomes 2a, but then times dA dt, chain rule, plus 100 squared. The derivative of 100 squared is not 2 times 100. 100 squared is just a number. Its derivative is 0. Derivative of c squared is 2c dc dt. Okay, and now we're ready to start plugging some things in. So let's see what happens here. So I've got my 2. I don't happen to know what a is at the moment. I'm just going to leave it blank. dA dt, I'm happy to copy that one as a dA dt because that's actually the question mark. So I'm happy that that's there. Plus 0 we won't write. Equals 2c. Okay, I don't have c at the moment, but dc dt I have. That was given as a 2. So this is times 2 over here. Okay, so is there any other information in the problem? Yeah, it's, where is it? 125 feet of string has been paid out. Okay, now we're ready to fix this thing at one moment in time when C is 125. And so we do get to plug in C equals 125 right now in that second set of parentheses. So C is 125 at this fixed moment in time, but what about A? Still don't know what A is. Well, at the fixed moment in time, we can find it. And so in the guidelines on pages 3 and 4, it talks about maybe redrawing the picture but making it static. And so this is what they were talking about. So it's an A down here and it's 100 here, but now it is a fixed 125 right there. And oh yeah, now we can figure out the value of A, which is groovy because that's the only thing we need. It's the only thing that's missing is A. So we do have our Pythagorean theorem. It's written right there. So it's a squared plus 100 squared equals c squared. So in this case, a squared plus 100 squared equals 125 squared. Not quite. Okay, so this is a squared. Let's put this in the way. A squared plus, that is 10,000. Equals, and then 125 squared, everybody knows that's 15,625. You knew that, right? And then we're going to solve for A, so A squared, just subtract here, so we get 5625. And then the square root of that. And the square root of 5625 happens to be a nice number. 5625, what is that? 75. So A turns out to be 75. I promise I didn't look those numbers up before turning the recorder on. I'm just so good. All right, next one. So A is 75, so we plug that right in here. I was being sarcastic, by the way. Yeah, the so good thing. Getting a little bit off my rocker being in this room for 9 straight hours lecturing to nobody. Okay, so I think that we're good. The only thing left in this equation that isn't known is dA dt, and that's exactly what we're trying to find. So we'll just solve for dA dt. You could cancel some 2's. That would be the most efficient thing, right? Divide both sides by 2. But I'll be lazy and just solve the equation in its current form. dA dt equals, so 2 times 125 times 2. Divide both sides by the 2 times 75. And now I suppose I should cancel, right? I shouldn't type that in. 125 and 75, they're both divisible by 25. So that gives me 5/3 and then times 2. So 10/3, and the units here were feet per something. Feet per second. Okay, so 10/3 feet per second is the rate at which the kite is moving at that one moment in time. Okay, if we're good there, we're moving on to the next one. Number 11, Boyle's law for gases states that PV equals C for pressure P, volume V, and a constant C. At a certain instant, the volume is 75 cubic inches, the pressure is 30 pounds per cubic foot, and the pressure is decreasing at a rate of 2 pounds per square inch every minute. At what rate is the volume changing at this instant? I have no idea what's going on, but I think this is actually going to be pretty easy. There's no picture to draw. It's just going to be symbol crunching. We don't need to define any variables. They're all given here. So it says the pressure is decreasing at a rate of 2 pounds per cubic per square inch every minute. So that means that the rate at which the pressure is changing is 2, except it's not 2 because it said decreasing. Got to make sure you catch that word and put a negative in front of your 2. Okay. And then it says that the volume is supposed to be 75 at the one moment and the pressure is 30 at the one moment. I'm just going to, I haven't really been writing those things at this spot in the problem, but I'm just going to write them. So at some point, the volume is 75 and the pressure is 30. Okay, and it says, at what rate is the volume changing at this instant? So that's our question mark, dB dt equals Question mark. And the only thing we can do is take a derivative of that equation. So let's do it. Derivative of both sides of that equation. Okay, so derivative on the left-hand side, p and v are both variables, which means that the rule we need to use for the derivative on the left-hand side is the product rule. P times v. First, times the derivative of the second. The derivative of v isn't just 1, it's dv dt. Time is passing. The plus rest of the product rule. Second, times derivative of the first. Derivative of p isn't just 1, it's dp dt. Equals, don't forget to take a derivative on the right-hand side. The derivative on the right-hand side is not 1. The derivative on the right-hand side is not even 1 times dc dt. It says that c is a constant. The derivative on the right-hand side is 0. Okay, and this is most excellent because look, we've got 1, 2, 3 things we're going to plug in, and the fourth thing is the unknown, and we're just plugging straight into this one. This is the easiest one so far. Okay, so p is 30 times dv dt, that's my question, plus the v at this moment in time is 75, times dp dt is -2. Again, that negative really important. 30 dv dt, move the 150 over to the other side, and then divide both sides by 30. dv dt is 150 over 30, or just 5. So the volume is changing by 5 cubic somethings. What is it? 5 cubic inches, I guess, each minute. Cubic inches per minute. A stone is dropped into a lake, causing circular waves whose radii increase at a constant rate of ½ of a meter per second. At what rate is the circumference of a wave changing when its radius is 4 meters? Okay, you can draw a picture if you want. It's just going to look like a circle. It says the radii are increasing at ½ of a meter per second. Super, that's dr dt. ½ of a meter per second. At what rate is the circumference changing? Excellent, that's what we want to find. dc dt. At the moment when the radius is 4. So at some point the radius is going to be 4 meters, although we can't fix that too early. So this tells me I need a relationship between the circumference of a circle and its radius. This is not an equation I would give you. I'm hoping you can pull that one out of a hat. The circumference is given by 2 times pi times r. And we're good to go to take a derivative of both sides with respect to time. Again, almost always time for related rates problems. The derivative of c is 1 dc dt. The derivative of 2 pi r is just 2 pi. That's the coefficient of the r. But then times dr dt. And again, we are given the values of 2 variables here. And we're just going to plug in and get our unknown. I didn't put a question mark there. Okay, so dc dt, that's the question mark. Equals 2 pi times, and then instead of dr dt, we can just put 0.5. And then surprisingly, the r has no place to go. Apparently that means that the r does not matter, that the circumference is going to change at the same rate regardless of how big or small this circle is, regardless of what the radius is. So we just multiply 2 pi times ½ and we get 1 pi, or just pi, and the units here are going to be circumference units over time units. And so those units here are meters per second. Circumference is always growing at pi meters per second at every moment in time. Okay, 31, this is the last one I'm going to do in this video. I also think it's the toughest one out of the 6. An airplane at an altitude of 10,000 feet is flying at a constant speed on a line that will take it directly over an observer on the ground. Okay, let's start drawing a picture here. So I've got our airplane up here. Use your imagination. Flying at a constant altitude of 10,000 feet. So altitude here to the ground, 10,000. And I'm not labeling that with like a variable. It's not an A or B. That is a constant 10,000. And it's going to fly directly over an observer on the ground. And so let's suppose that the plane is flying this way and the observer is down here on the ground. Again, use your imagination. And it says, just to be clear, this thing looks like it's like going slightly uphill. It's not, right? It's got to stay at a constant altitude. So really going straight left. I cannot make this thing go straight. How's that? Okay. So it says at a given instant, the observer notes that the angle of elevation of the airplane is 60 degrees and is increasing at a given rate. Okay, so we don't have a label for the angle of elevation. We got to put a theta in this picture. And so you should know that the angle of elevation is defined to be the angle between horizontal and the line that the person is looking at. So this observer is looking at the plane this way. So I'm drawing in that line. It feels like maybe Pythagorean theorem here, but that is not right. We are going to label the angle of elevation. Again, it's the angle between the horizontal and the line that the observer is looking at. So it is this angle right here. That is the angle of elevation. And it says the angle of elevation is 60 degrees at one moment in time and is increasing at a rate of 1 degree per second. So the theta dt is 1 degree per second. And I'm not going to put the theta equals 60 just yet because I don't want to fix it at this moment yet. I'll put in the 60 later on. But it says we're trying to find the speed of the plane. Okay, just like the kite that was only moving on the same horizontal line, the speed of the airplane is just how fast it is going horizontally because there's no vertical component. It's not going off at an angle. And so the speed of the airplane is really just going to be how fast the length of this line is changing. And so I feel like we need to therefore give a name to the length of that line segment. So how about we call this one here, I don't know, x. So x can be the length of that line segment, and then the speed is just the rate at which x is changing. So dx dt is the thing we're trying to find. It's going to be in feet per second. Okay. So we are interested in information about x, and we have information about theta, and there's actually more information about theta. And so we want an equation that relates x and theta. And again, I said maybe Pythagorean theorem because it's a right triangle, but you don't know anything about the green length, and you don't care actually about the green length. And anyway, Pythagorean theorem does not relate to the angle. And so we need an angle equation. And the equation we're going to use is one of our trig functions. With respect to theta, this 10,000 is the opposite side, and this x is the adjacent side. And so the magic equation is going to be the trig function that relates opposite to adjacent, and of course that's tangent. So we know tangent of theta is opposite over adjacent, 10,000 over x. So there's our magic equation. And I'm ready to take a derivative of that magic equation right here, right now. So we know the derivative of tan stuff, that's secant squared of the stuff, but theta is not the independent variable, it's time, and so of course we multiply by d theta dt equals derivative of 10,000 over x. You could use the quotient rule, but I remember the derivative special case for constant over x is just negative the constant over x squared times, and then again, x is not the independent variable, so derivative of the stuff, derivative of x with respect to time. Okay, I am reasonably happy with this equation, but I'm not thrilled. The d theta dt, I know that one. That's 1 degree per second. The x dt, I want that one, so I'm happy that that's there, but I'm not thrilled that there's an x and a theta. Okay, wait a second. At some moment in time, the theta is 60. Okay, this seems like a good moment to write down theta is 60 degrees at this one moment in time. So then I'm happy with this one. I can just put 60 in. But what I don't yet have is this. I don't yet have a value of x. And so how are we going to find the value of x when theta is 60? Well, I'm just going to redraw that picture. But instead of making it all variable, all dynamic, I'm going to make it static. So where can I squeeze this thing? About over here. So at the static moment in time, okay, so this is always 10,000 no matter what. 1,000, and then we know this is a 60-degree angle, and x I'm going to label as x, but we can actually find the value of x here using trigonometry. In fact, using this tangent theta equation. Tangent of 60 is supposed to be 10,000 over x. Great. Let's find x. Tangent 60 is 10,000 divided by x. Tangent of 60, probably I should know that one, right? Is that radical 3? So tangent of 60, yeah, I think radical 3 is good there. And we're trying to find x, so let's get the x over to the other side. So x radical 3 equals 10,000, and then divide both sides by radical 3. So x is 10,000 over radical 3. Lovely. Now I think we have everything we need for this black equation. So we're going to start plugging in piece by piece. Okay, secant squared. We're just putting 60 in here. So secant squared of 60 degrees times d theta dt. That was given. I think it was just 1 degree per second. 1 degree per second right there. I'm going to leave a 1 degree per second. Yeah, so it's actually just a 1, like that SEC is seconds, not secant. I'm going to leave a suspicious blank space right there. And then continuing this equation, negative 10,000 over x squared. The x we just found in blue at the bottom right, it is 10,000 over root 3, but remember it is x squared. So that one needs to get squared. And then dx dt, I think that was what we wanted, right? We're looking for the speed of the plane. So I'm happy to have a dx dt in this equation. Okay, so there's just a tiny bit of work left to do here. We need to get dx dt by itself. We need to evaluate secant squared of 60 degrees. Neither of those is a big deal. But what is a big deal is that suspicious blank. Earlier this semester, several times I think, we have said that calculus is done exclusively in radian mode. Exclusively in radian mode. And the reason that we do that is because in radian mode, the derivative of sine is cosine, but in degree mode, the derivative of sine is cosine times pi over 180. And who wants to multiply every single trig derivative by a pi over 180? Not me. So this problem was rather sneaky, giving us stuff in degrees. So the problem here actually isn't the 60 degrees, because if you do, so down here, we're going to do secant squared of 60. Okay, so secant squared of 60 degrees is exactly the same as secant squared of the corresponding radian version of 60 degrees. That's pi over 3. Secant squared of pi over 3 in radians is exactly the same as secant squared of 60. So actually this part we could care less about. We're going to get the right answer there. But it's right here. This 1 degree per second is no good. It needs to be in radians per second. And the reason that we need to make that conversion is that when we said that the derivative of tangent was secant squared, we made this problem in radians. If we had done the derivative of tangent in degrees, we would not have gotten secant squared. We would have had to multiply by some correction factor. So very sneaky, but again, all of calculus in radians. So if you see something in degrees, your lower calculus radar should go up. So we need to multiply 1 degree per second. Let's remember here, let's go purple. Okay, 1 degree per second equals 1 degree per second. So remember, the way to convert between radians and degrees is to multiply by either 180 over pi or pi over 180. I can never remember which one is which. I just know I need to follow my units. I need degrees to cancel. So apparently we need the 180 degrees down there, and therefore the pi radians upstairs. And so the degrees cancel, and the 1 you don't even need to write, but pi over 180 radians per second, that's what we should have put. Not 1 degree per second, but rather pi over 180 radians per second. I'm not going to write the units here, but we certainly needed them before because we had a problem leaving it in degrees per second. Okay, so I'm going to come up here, 1 degree per second. I'm going to say that this is equal to pi over 180 radians per second from our work down below. Okay, so I think we are in a good place to finish this one now. Let's bring it home. Okay, so we need secant squared of 60 degrees, so that's an evaluation thing we need to do. I don't know secant of anything. I do know that secant is the reciprocal of cosine, and I know that cosine of 60 degrees is root 3 over 2. So that means that, let's do a color here. That means that, okay, so we said cosine was root 3 over 2. Is that right? make sure. Cosine of 60. I don't think I have that right. Cosine of 60 is a half. So then secant of 60, instead of being 1/2, should be 2/1. It's the reciprocal of cosine of 60. But this is secant squared, so it needs to be squared. And then I'm going to copy my pi over 180. That's my correction factor. Equals, okay, let's clean this thing up here. I've got negative 10,000 on the top, divided by. Now I'm going to square both things in the parentheses here. I'm just going to write it as a 10,000 squared. And then the radical 3 gets squared, so that's just going to become plain 3, but it's in the bottom of the denominator of my fraction. So I'm going to multiply top and bottom by 3 and discover that that 3 really belongs up on the top. And then dx dt, again, is the question mark, so that one is fine in our equation. Okay, almost done. Really hope we didn't make any mistakes here. Okay, so we got 4 pi over 180 equals, so one of those 10,000s cancels, so I see a negative 3 over 10,000 dx dt. And so solving for dx dt, we're going to multiply both sides by negative 10,000 over 3. So it was a 4 pi over 180. We're going to multiply by negative 10,000 divided by 3. Okay, and then we'll just reduce here a little bit. The 4 and the 180 reduce to 1 and 45. And then we can multiply the 45 by the 3. And this will make it agree with the answer in the scanned key. So negative 10,000 pi divided by 135. And the units here are whatever they were. We didn't change any units other than that degree nonsense. So what do we have here? Find the speed of the airplane. Okay, so it's seconds and feet per second. Apparently, if you type this into a calculator, I'm just going to read off of the key here. We get 232.7. 232.7 feet per second. Why is it negative here, whereas the answer in the key is positive 232? Well, so this question technically is asking for the speed, right? Speed of the plane. Speed is always a positive number, so we should just take the absolute value of our answer. If it said velocity, then I think our negative makes sense, assuming that this particular plane says it's going to take it on a line that will take it directly over the observer. So I think we were right when we said the plane was heading towards the observer. And so in a very real sense, you could say that this distance here is decreasing at 252-ish feet per second. So his speed is negative 252 feet per second, but anyway, it's speed, so we can make it positive. Okay, so don't forget there is one other problem in the homework. It's in your textbook. I'm not doing it here in this video.